Hello, good morning. I'm Nazmus Ashrafi, and I'm here with my co authors, Professor Midiani and Professor Buktif. We are from UAEU University. We built LEOPARD, a framework to stop LLMs from overcorrecting student grammar. Let me begin by showing you the problem. So a learner writes, I arrived to the station and I was late because of the traffic. A human tutor would circle two errors, from to at, and insert the missing word of. Two minimal edits. GPT-4 returns, I reached the station, but unfortunately arrived due to heavy traffic congestion. The whole sentence is gone. We call this the fluency paradox. LLMs are pre-trained to maximize fluency, and instruction tuning makes them eager to rewrite. So every unnecessary change becomes a false positive and the precision collapses. You cannot just prompt your way out of this. We tried. We discovered that smaller models are safety first. High precision, low recall, they miss complex errors. LLMs are fluency first. High recall, low precision, false positives everywhere. The key insight is the structural constraint paradox. If you prompt, preserve original structure, you either kill recall or the model ignores the constraint. Small models, as you can see on the top, and the large models are over here. Our goal with LEOPARD is to reach this stage where we have high recall and precision. Instead of fighting overcorrection, we let the LLM generate freely first and then filter using a lower powered LLM. So we have two agents. The boss agent, which is powered by a large model like GPT 4.1, generates the most fluent correction it can. The purest GPT 4.0 mini, which is a smaller and cheaper model, evaluates each individual edit and vetoes anything that isn't grammatically necessary. The critical step is that we use errand to decompose the boss's overcorrected output into atomic edits. Instead of judging, is this sentence good, which is intractable, we ask, is this specific two-word change necessary, which is tractable? This is the pipeline, as you can see. The student sentence enters the boss, which generates overcorrected fluent corrections. The errand then extracts the atomic edits with original span, corrected span, and error type. Each edit then hits the purest three-stage cascade. The first stage is the fast pass. Punctuation, spelling, orthography, all these problems are auto-approved. No LLM calls needed. This saves compute because we already know that these kind of problems, they do not need to be vetoed. Stage 2, the heuristic filter. This checks the expansion length and the Levestein distance. If the corrected spans share very few characters with the original, it flags it as a stylistic rewrite. But close words like prepositions are whitelisted. For example, into at shares 0 characters, but is a valid fix. So we designed a whitelist dictionary which omits the word from the heuristic filter. Third stage, it goes to LLM as a judge, which is the GPT 4.0 mini with strict rubrics. If the original is already correct, even if it's informal, it vetoes the edit. Finally, only allowed edits are applied. Vetoed edits are reverted to preserve the student's wording. Let me walk you through a real-life example of what the system outputs. So the student writes, their love has finished because unknown reasons. The boss outputs, their love has ended due to unknown reasons. So there are 4 edits which are detected through the system. Edit 1, arrives to, is changed to reached. This is vetoed because it's low Levestein distance and correctly marked as a stylistic correction. Similarly, the second edit from finished to ended has detected that there is a low Levestein distance between these two, and because of that, the heuristic flags it as a stylistic edit correctly. The third edit, because to due to, as you can see, it goes through a closed class word, it passes the whitelist, and then it goes to the vetoed, the LLM as a judge. Over here, because is valid, so it does not need to be changed as due to, and the LLM as a judge, it detects it and it vetoes it. The last edit, missing off edit, this passes stage 3 correctly, and the LLM as a judge, which is the GPT-4o mini, confirms this error is due to it's a genuine error, and it allows the edit to stay. Final output, their love has finished because of unknown reasons. Only the real errors are fixed. The student word choice is preserved. Finally, we come to the results, and we can see that we on our benchmark that we tested, the CLC FC benchmark, which are real L2 exam scripts, we chose 100 records, and we use F0.5, which is basically it weights precision 2x over recall. As you can see, our results have improvement all across the board. One surprising find was that the recall was also increased because we believe that atomic decomposition preserves true corrections that get corrupted in monolithic rewrites. Leopard disangles this valid edits from invalid one, which is a counterintuitive finding in our results. Finally, if we see the error breakdown, you'll see that the precision stays flat at 0.5, which validates our closed class whitelist. The missing determiners improved by 12.5%, and noun replacements gained by 25%, exactly where LLMs make the most stylistic swaps. So the big takeaway is that 14% improvement by architecture alone. This suggests towards a broader principle. Reliability in generative AI can be achieved through orchestration, not just training. Finally, as you can see, we have certain limitations. We use 100 record subsets, but we report across 3 consistent runs. In our future work, we want to increase the number of samples that we test against, but we also want to mention that our study is theoretically grounded, which is by the Smith's noticing hypothesis from 1990. Learners needs conscious attention to form. LLM rewrites are implicitly recast. Leopards produced explicit corrections, targeting edits that looks like what a tutor would circle on a paper. Finally, to conclude our contributions, we define 3 fluency paradox, propose the dual agent boss purist architecture with neurosymbolic veto cascade, and demonstrated an improvement of 4.6 F0.5 improvement with no fine-tuning. Thank you. We present our source code in GitHub. I'm happy to take any questions. Thank you.